Okay, so our today's topic is D and F block elements, and we will do this chapter by question and answer. Okay, first question is what is meant by lengthenoid contraction? Because it is D and F block element, so lengthenoid and actinoids belongs to F block. Now, question is what is meant by lengthenoid contraction? Actually, in lengthenoid there is 4F, filling of 4F, 5D and 6S. In lengthenoid elements, there is a filling of 4F, 5D and 6S subshells. Okay. F subshell of the fourth shell, D subshell of the fifth shell, and S subshell of the sixth shell. So when we go on from lanthanum to lutetium, there is filling of electron in the 4F orbital, means inner orbital. And the shielding of F is, what is the shielding order? We shield most. What is the order of shielding effect? Maximum shielding is shown by S, then P, then D, and then F. So shielding of F is minimum. That's why effect of nuclear charge is more. Effect of nuclear charge is more than that of shielding of because see, when electrons are filled in different shells, so one electron and one proton is added at the same time. One electron is added and one proton is added. So in lanthanoids, there is a filling of 4F. Okay. So when electron is filled in F and shielding is poor, so effect of nuclear charge is more. And that's why there is a decrease in size along the series, but it decreases steadily. Okay. And therefore this steady decrease in size, ionic radius, from lanthanum to lutetium, that is termed as lanthanoid contraction. Simply, steady decrease in the ionic radius as atomic number increases. You can write. Don't remember lanthanum and lutetium. Just write the steady decrease in the ionic radius of lanthanoid ions as the atomic number increases. That is called lanthanoid contraction, and it is due to imperfect shielding of imperfect shielding of imperfect shielding of F electron. Okay, that is called lanthanoid contraction. Yes, beta. Did you get it? Okay. Next question. So simply, if question is there, what is lanthanoid contraction and what is its cause? You write the steady decrease in the ionic radius of lanthanoid ions, or steady decrease in the ionic radius from lanthanum 3+ to lutetium 3+ is termed as lanthanoid contraction, and it is due to the imperfect shielding of F or electrons, F subshell electrons, or you can write F electrons simply. Question number 2. why do transition elements show variable oxidation states? So say, in D block elements, what is the general electronic configuration? General electronic configuration of D block elements. So general electronic configuration of D block element is n-1d 1 to 10 and ns 1 to 2, or sometimes it is 0 to 2. Okay, n-1d 1 to 10 or and ns 1 to 2, or if you include palladium, that is ns 0 to 2, because in case of palladium it is krypton, yes, 3d, or sorry, it is krypton 4d 10 5s0. So to include this, general electronic configuration is n-1d 1 to 10 ns 0 to 2. So in case of transition elements, n-1d electrons as well as ns electrons, both are involved in bond formation. They are involved, and that's why they have, and because they have approximately equal energy, so both are considered as valence electrons. That's why they have variable oxidation state. So see, the variability of oxidation state of transition element is due to incompletely filled d orbitals and presence of unpaired electrons ns and n-1d electrons, which have approximately equal energy, and both will participate in bonding. Simply you can write that when write this one due to participation of n-1d and ns electrons in bonding, they have variable oxidation state. And why they participate, both can participate, because both have almost equal energy and both are treated as valence electrons. Okay, next question. Write the formula of an oxoanion of manganese in which it shows the oxidation state equal to its group number. So see, what is the electronic configuration of manganese? It is argon 3d5 4s2, and because its atomic number is 25. Now, how do we calculate group number in case of D block elements? Group number is equal to number of n-1d plus number of n-1d electrons plus number of ns electrons, and number of electrons in n-1d orbital is 5 and number of electrons 4s is 2, so it is 7. Is 7. So group number is 7. So manganese can form MnO, it can form Mn2O3, it can form MnO2. Okay, but it is oxoanion. Okay, oxoanion, so it can form MnO4 negative as well as MnO4 2 negative. So MnO4 negative, manganese is X, take it as x, oxygen as -2, so it is x minus 4 to the 8 equal to -1. So x is +7. So in permanganate, MnO4 negative is permanganate. Its oxidation number is +7. Its group number is 7. So this is the ion with oxidation number +7. Now, but in the case of this is manganate ion. X minus 2. X minus 8 equal to -2. That is x equal to +6. X is +6. In this case, group number is 7, but number is of manganese is 7, but its oxidation number is +6. So an ion, oxo anion of manganese, in which its oxidation number is equal to group number, that is permanganate. And you can draw its shape. MnO4 negative is tetrahedral. This is permanganate, and this is manganate. Okay. So simply write permanganate ion, that is MnO4 negative with oxidation number +7. This one is actually MnO4 -1. The charge on MnO4 negative, MnO4 is -1. That is called permanganate ion, like potassium permanganate, KMnO4, most common oxidizing agent. Potassium permanganate, that is an oxidizing agent. Oxidizing agent in acidic medium, basic medium, as well as neutral medium. Oxidizing agent in acidic, basic, as well as neutral medium. And at the same time, one more thing I would like to tell you, that potassium permanganate is pink in color. Color is pink, but that color is due to charge transfer spectra. From ligand, oxygen is taken as ligand, and manganese is a metal. So ligand to metal electron transfer takes place. P pi D pi star. But for this question, you can write simply permanganate ion with oxidation number +7. That is the oxo anion of manganese, in which it shows the oxidation state equal to its group number. Next, what happens when ammonium dichromate is heated? This is ammonium dichromate. Now, in ammonium dichromate, you can see this is NH4 plus, and these are two ions. See, NH4 plus, that is called ammonium, and Cr2O7 2 negative, that is called dichromate. That's why it is called ammonium dichromate. Okay, Now when it is heated, this question is from D and F block element as well as P block elements, because nitrogen belongs to P block, chromium belongs to D block. That's why this question is in the both, and well it is in the preparation of nitrogen, because ammonium dichromate, when we heat it, it gives N2, Cr2, O3 and water. It is in crackers. Ammonium dichromate is filled in crackers, because when we heat it, nitrogen gas is evolved that give upthrust to the rocket, and Cr2O3 green in color. Just balance it. I think now it is balanced. So this is the balanced chemical equation. That when ammonium dichromate is heated, then we have N2, Cr2O3 along with 4H2. Write the formula of an oxoanion. Again, write the formula of an oxoanion of chromium, in which it shows the oxidation state equal to its group number. Cr2O7 2 negative, it is dichromate ion, in which oxidation state of chromium is +6. This Cr2O7 2 negative. And if we see chromium, its atomic number is 24, and it is general electronic configuration. Sorry, electronic configuration is 3d54s1. I will write for 3d. Okay, for 3d series, you can remember, see, scandium, that is 21, titanium 22, vanadium 23, chromium 24, manganese 25, iron 26, cobalt 27, nickel 28, zinc is that 30, argon is 18. This at least 3d series you have to remember. Okay. So scandium is 21, so it is 3d1 4s2, titanium 3d2, see 22 3d2, 23 3d3 4s2. Chromium and copper, they are exceptions. Accept them. Rest is same. 3d5 4s2, 26, it is 3d6 4s2. Cobalt 27, 37, 28, 3d8 4s2, 10 4s2. Now chromium and copper, they are only exceptions. See, rest is 21 3d1, 22 3d2, 23 3d3, 25 3d5, 26 3d6, 27 3d7, 28 3d8, 30 3d10. So 24 it is 3d5 4s1 and 29 3d10 4s1. These two are exceptions. Except them, all have normal electronic configuration. Why chromium and copper are exceptions? Because they have exactly half-filled electronic configuration, 3d5 and 4s1. After one electron is transferred from 4s, it becomes exactly half-filled, it becomes exactly fully filled. That's why chromium and copper are exceptions. That is the question from class 11, right? So keep in mind these electronic configurations. So now chromium is argon 3d5 4s1. So it can have group number. What is group number of d block elements? Number of n-1 d electrons plus number of ns electrons. That is 5 plus 1. That is group number is 6. Now for Cr2O7 2 negative, you can write like this. Chromium, take it as X, oxygen as minus 2. So it is 2x minus 14 equal to minus 2. That implies 2x equal to minus 2 plus 14. That is plus 12. So x is equal to plus 12 by 2. That is plus 6. So oxidation number of dichromate ion, that is plus 6, and group number of chromium is also 6. So dichromate ion is one in which oxidation number of chromium is plus 6, which equal to its group number, that is 6. Now second oxoanion of chromium is chromate, CrO4 2 negative. This is chromate ion. Now chromate ion, what is the oxidation number of chromate ion? So its oxidation number X is again plus 6. So that means oxoanion of chromium in which it shows oxidation number equal to its group number, that you can write chromate as well. Chromate and dichromate both have oxidation state, group number 6, and oxidation state of chromium in both of them is plus 6. Let us write their structure. So chromate, it is this chromate, and in dichromate so it is chromate and dichromate structure. In dichromate, two tetrahedra are joined together by a common oxygen. Okay, and CrO4 2 negative, that is simply tetrahedral in shape. Next, generally there is an increase in density of elements from titanium to copper in the first series of transition elements. So obviously there is an increase, because as we go from titanium to copper, there is an increase in mass, and at the same time decrease in size, because from titanium to copper, that is in the 3D series, as atomic number increases, atomic size decreases, mass increases, and size is volume decreases, so obviously density will increase, because mass is increasing, volume is decreasing, so density will obviously increase. So see, from titanium to copper, the atomic size of the elements decreases, because as we go along the period, atomic size always increases with few exceptions, and mass increases, as a result of which density increases. Next, transition elements and their compounds are generally found to be good catalysts in chemical reactions. Now, catalyst. So what is the role of catalyst? Catalyst will, what catalyst do? Yes, beta. What is the role of catalyst? Very good. It will increase the rate of reaction. So most of, say in the case of hydrogenation of alkene, platinum, palladium, copper, sorry, nickel, platinum, palladium, they will be used as a catalyst. Nickel, palladium, platinum. Okay, this reaction. Okay, hydrogenation. There are many reactions in which transition elements or their compounds, they are used as catalyst. So why, especially what is special in a D block elements? So it is due to, first, they can provide surface area. Their large size, they can provide, like in this case, they provide surface area for the reaction to take place. Second thing, they have incomplete, or we can say they have unpaired electrons and have incomplete d orbital, and they have an ability to form complexes. They have ability to form complexes, and at the same time they have variable oxidation state. So these 5 points you can incorporate. Like in this question, answer is written as catalytic properties of the transition elements are due to the presence of unpaired electrons, right? Due to the incomplete d orbitals, right? Their unpaired electrons in their incomplete d orbitals, they have variable oxidation state. They have, at the same time they have tendency to form complexes. They have tendency to form complexes and can provide surface area for the reaction to take place. So these are the points that could be written while answering this question, because and it is very common question. Why transition elements and their compounds are generally found to be good catalysts in chemical reactions? You can write because they have unpaired electrons, they have incomplete d orbitals, they can form complexes, they have variable oxidation states, and they can provide surface area for the reaction to take place. Next question. Explain the following observations. Transition elements generally form colored compounds. Transition elements, they generally form colored compounds. So why they form colored compounds? Because they have unpaired d electrons. Again, presence of unpaired electrons. Same, due to the presence of unpaired electrons, they are paramagnetic in nature. Most of the transition elements and their compounds are paramagnetic. Again, due to the presence of unpaired d electrons. So because because of the presence of unpaired electrons, they undergo DD transition by absorption of energy. They undergoes DD transition by absorption of energy from visible region. And then emitted light shows a complementary colors, and that's why transition elements form colored compounds. So let's go in detail how this DD transition takes place. Actually, if we talk about transition and metal complexes, they are either octahedral or tetrahedral. So I am talking about octahedral complexes. Octahedral complexes. So octahedral complexes are metal attached to 6 ligands. Metal is attached to 6 ligands. Okay. Right. So where these ligands are located, just say the location of ligands. This is z-axis. These are 2 ligands on the z-axis, and all are at 90 degree. Obviously, all the ligands are on the line which are perpendicular to each other. That means they form Cartesian coordinates. Let us say this is x-axis, this is y-axis. So that means all the ligands are on the axis. Ligands are on the axis. In octahedral complexes, ligands which are attached to metal, what are ligands? Which can provide electron pair, which can donate an electron pair, that is called ligand, like ammonia. Okay, water. They can provide a lone pair of electron to the vacant orbital of metal, that is called ligand. So all the ligands are on the axis, okay, which provide electron to the metal. Now, what about the shapes of d orbitals? So d orbitals so shapes now dxy, dyz, ezx. So dxy, in the lobes are in between the x and y axis. In dyz, lobes are in between the y and z axis, and in dzx, lobes are in between the z and x axis. Now dx square and y square, dx square minus y square. Ligands are, sorry, lobes are on the axis. dz square lobes are on z axis. In dx square minus y square, lobes are on x and y axis. So in this case, sorry, lobes are on the axis. dxy, dyz and dzx, lobes are in between the axis. Lobes are in between the axis. So see, ligands are on the axis, lobes of dx square minus y square and dz square are on the axis. So they are head on to each other. As they are head on to each other, they can repel more, and that's why degeneracy of the d orbital is removed. See, these are d orbitals, 5d orbitals which are degenerate. Degenerate d orbitals. Degenerate means the orbitals having, yes beta, tell me. Degenerate means, degenerate orbital, what it means? Degenerate orbital means, degenerate orbital means the orbitals having same energy. Okay, orbitals having same energy. So see, all the 5d orbitals are degenerate in the absence of ligand. In the in the absence of ligands. But in the presence of ligands, these d orbitals split, removal of degeneracy. Removal of degeneracy and d orbitals which are in between the axes. The ligands are head on to dx square minus y square and dz square. As they are head on to it, therefore their energy will increase. Ligands or lobes are head on to each other. So their energy increases, and these two orbitals are called EG, doubly degenerate orbitals. And dxy, dyz, and dzx, their energy decreases, and this is called T2G. So they split into two classes, T2G and EG, and the difference is called delta O. Difference is called delta O, right? Here removal of in the presence of ligands. The presence of ligand, there is removal of degeneracy. Okay. So whenever there are unpaired electrons, see, whenever there are unpaired electrons, because of this energy difference, and this energy difference lies in the visible region. So when electron, let us say it has only one electron, T1. So one of the electron is in the T2G. So when it absorbs energy in the visible region, electron moves from T2G to EG, and therefore energy is absorbed in the visible region and complementary color is seen by us, and that's why that complex, that compound appears color to us, that ion appears color to us. This is the reason. That is called DD transition. See, because of the presence of unpaired electrons, unpaired d electrons, which undergoes DD transition. So this is due to that DD transition takes place from visible region, and then emitted light shows complementary colors, and this is how transition elements form colored compounds. Next question. Zinc is not regarded as a transition element. Not only zinc, cadmium and mercury, they are not regarded as transition elements, because what are transition elements? Which have incompletely filled, which have partially filled d orbital, n-1 d orbital in its ground state or in any of its commonly occurring oxidation state. Let us write the statement definition. What is transition element? Transition elements are the elements which have partially filled n-1 d subshell in its ground state or in any of its oxidation state, that is called transition element. So if we see zinc, cadmium, zinc is 3d10 4s2, cadmium is 4d10 5s2. So zinc has only +2 oxidation state, so it is 3d10 only. Cadmium also have only +2 oxidation state, so it is 4d10 only. So that means zinc, cadmium as well as mercury all have fully filled d orbital in its ground state as well as in its oxidized state. That's why they are not regarded as transition elements. See, zinc in its common oxidation state of +2 has completely filled d orbitals, but what we require? Partially filled d orbital. So it has completely filled d orbital. That's why it is considered as non-transition element. It is not regarded as transition element. Next question. Copper 1 ion is not known in aqueous solution. See, otherwise if you see copper 1 plus, copper is 3d10 4s1, copper is 3d10 4s1. So in its +1 oxidation state, chromium is 3d10. That means it has fully filled d orbital in +1 state, so it should be stable, but it is stable in gaseous state. But copper 2 plus, which has partially filled d orbital 3d9, it is stable not in aqueous gaseous state but in aqueous solution. If you compare copper 2 plus aqueous, so copper 2 plus aqueous is more stable than copper 1 plus aqueous. What is the reason? Reason is when copper 1 plus gaseous is converted into copper 2 plus gaseous, obviously there is absorption of energy. Electron is removed and energy is absorbed, and that is second ionization enthalpy. But at the same time, when copper 2 plus interact with water, its hydration enthalpy is more than the energy absorbed. Hydration energy means amount of energy released when ion interact with the 1 mole of ion interact with the water. So energy released is more in aqueous solution. Hydration energy is more than the second ionization enthalpy of copper, and that's why overall energy is released. That means overall it becomes stable. So what we write, it is due to high hydration enthalpy of copper 2 plus ion. And that's why copper 1 plus aqueous undergo disproportionation. What is disproportionation? Yes, beta. What do you mean by disproportionation? Disproportionation means if the same element gets oxidized as well as reduced, that is called, that ion is, or that compound is disproportionated. What is disproportionation? Disproportionation reaction. The reaction in which same element or compound or ion undergoes oxidation as well as reduction, that is called disproportionation. So copper 1 plus aqueous undergoes disproportionation because copper 2 plus aqueous is more stable than copper 1 plus aqueous. So this is the reason. So see, copper 2 plus aqueous is much more stable than copper 1 plus aqueous because although second ionization enthalpy of copper is large, that is true because 3d10 to 3d9 is fully filled d orbital becomes partially filled. So stable to unstable. So obviously huge amount of energy is required. That is large. But at the same time, hydration energy of copper 2 plus is much more negative than that for copper 1 plus aqueous. And therefore, it is more than compensates for the second ionization enthalpy of copper. And that's why many copper 1 compounds are unstable in aqueous solution and undergoes disproportionation as well. It is copper 1 plus aqueous, copper 2 plus aqueous, copper solid. Next is actinoids exhibit greater range of oxidation states than lanthanoids. Actinoids and lanthanoid. You know, in lanthanoid, there is a filling of 4F, 5D and 6S. And in actinoids, there is a filling of 5F, 6D and 7S. So keep in mind, energy difference is very, very less. They are almost of same energy in case of actinoids. 5F, 6D, 7S. That's why all of them participate in bonding. They are involved in bonding. And that's why actinoids show variable oxidation state and lanthanoid can show +3, +2 and +4 only. But they can show up to +6, +7. Okay. See, because of very small energy gap between 5F, 6D and 7S subshells, all their electrons can take part in bonding and therefore they show variable oxidation states. Right? Next. Question number 9. Assign reasons for each of the following. Transition metal generally form colored compounds. We have just discussed that why they form colored compounds, because they have unpaired electron. Most of them have unpaired d subshell, unpaired electrons in d orbital. They have unpaired d electrons and therefore they undergo dd transition. So energy is absorbed and energy emitted is shown to us as a complementary color. See, because of the presence of unpaired d electrons which undergoes dd transition by absorption of energy from visible region and then emitted light shows complementary colors. And just now I have shown this splitting of d orbitals T2G and EG in octahedral field or octahedral complexes. So that the transition of electron from T2G to EG, that is in the visible region, and that's why they are colored. Next, manganese exhibits the highest oxidation state of +7 among the 3D series of transition elements. What is the reason? So, in manganese, 3D5 and 4s2. Manganese is 3D5, 4s2. So all the p electrons are unpaired. When 4s electrons are removed, along with that, we can remove all the 3D electrons one by one. That's why it can show oxidation state from +2 to +7. The manganese exhibits highest oxidation state of +7 among the 3D series of transition elements because all the oxidation states are exhibited from +2 to +7 by manganese. No other element of this series show the highest state of oxidation except manganese. Chromium can show up to +6 because it is 3D5 4s1. So manganese is the only one can show oxidation state from +2 to +7. Last question of the day. Question is, how would you account for the following? First is chromium 2 plus is reducing in nature, while with the same d orbital configuration D4, Mn3 plus is an oxidizing agent. See, chromium 2 plus, chromium plus 2. First I will write electronic configuration of chromium and manganese. Chromium is 3D5 4s1. Manganese is 3D5 4s2. So see, chromium 2 plus. What is chromium 2 plus? 3D4. And chromium 3 plus, it is 3D3. So see, chromium actually oxidizing or reducing nature is shown in aqueous solution. So in aqueous solution, water is the ligand. Therefore, they split like T2G, EG. Okay, so say it is like this 3D5, but in Cr3 plus it is 3D3, so it is like T2G3, exactly half-filled configuration in T2G, that is more stable. That's why chromium 2 plus can easily convert into chromium 3 plus by losing one electron, so that it become more stable. That's why it is reducing in nature. The one which can lose electron easily act as a reducing agent. But if you compare with Mn, so Mn3 plus, it is 3D4, but if it gain one electron, then Mn2 plus becomes 3D5, because losing electron from 3 plus is difficult, but gaining electron is easier because Mn is 3 plus. So 3 plus can gain electron and become more stable, exactly half-filled configuration. That's why Mn3 plus is an oxidizing agent because it can gain electron easily, and Cr2 plus is reducing in nature, which because it can lose electron easily. So see, chromium 2 plus has configuration 3D4, which easily changes to D3 due to stable half-filled T2G orbitals. It is T2J3, Eg0. Therefore, chromium 2 plus is reducing agent, while Mn2 plus has stable half-filled D5 configuration, and therefore Mn3 plus is easily changes to Mn2 plus and acts as an oxidizing agent. Next question. In a transition series of metals, metal which exhibit the greatest number of oxidation states that occurs in the middle of the series, because in the middle of the series there are maximum number of unpaired electrons. Because in the middle 3D has all the 5 electrons. Example is manganese. Okay. Due to the presence of more number of unpaired electrons and use of all 4s and 3d electrons in the middle of the series, they exhibit greatest number of oxidation state. And best example is quoted by manganese. It is 3d5 4s 2. Manganese is 3d5 4s2. So manganese, this case 3d, it has 5 electrons, 5 unpaired electrons, and all will participate in bonding. Therefore, manganese can show +7 oxidation state. None of the other element can show up to this oxidation state. So that's all for the day. Any doubt, beta? Okay, then thank you. Yes, beta. Okay, same time, 6 o'clock. Yes, beta. So today we have a session of D and F block elements. This was the first lecture of D and F block elements. We will complete whole NCERT theory in question answer format, because in D and F block elements there are questions of 1 mark and 2 marker. Most of the questions are of 1 marker. 5 marker questions, there are 5 questions of 1 mark each. Okay, there are sub top parts. Okay, so D and F block elements we will do by question and answers completely. I make you understand this chapter, and along with that we are doing this class 11 as well as class 12 NCERT concept, NCERT exercise, NCERT in text questions, NCERT example even, and then we will do NEET and JEE questions. All of this, the complete package, free of cost. Who join, ask your friends to join and support my channel. Just share your friends that they will be benefited, and support my this free education drive. I will definitely help you crack exams like NEET, JEE, and at the same time I promise you that you will score good marks in your board exam. Join and ask your friends to join. Thank you. Support me and my channel.